Thank you everyone for joining this virtual talk, which we're hosting as part of the MIT Club of Australia. I think there might be some people who don't normally join our activities dialing in from the United States. Welcome. We have virtual talks every month or sometimes every second month, and I believe that you can see them through the MIT website, so we always welcome other alums to join our talks. For those of you who don't know me, my name is Evelyn Mervine. I am the Alumni Regional Ambassador here in Australia. I've lived in Australia for 6 years, and I'm a dual American-Australian citizen. I graduated from MIT in 2012 with my PhD in course 12. And for those of you who don't have all of the numbers memorized, that's Earth, Atmospheric, and Planetary Sciences. It is a huge honor to have Larry James, first of all, here in Australia, and now a very active member of our club, which is fantastic. And he has volunteered to give one of our virtual talks today. Lieutenant General Larry James is currently here in Australia with 2 positions. He's a strategic advisor for the SmartSat Cooperative Research Centre in Adelaide. He's also a distinguished professor of space research and innovation at Monash University. Previously, before he moved here to Australia, he was in a role as Deputy Director and Chief Operating Officer of NASA's Jet Propulsion Laboratory, and he was in that role from 2013 to 2024. Prior to that, he had a very long and distinguished career in the US Air Force, including a position where he was working at the Pentagon and supervising a large number of people. In terms of his education, importantly, the reason why he's connected to MIT, he has an MSc degree in aeronautics and astronautics from MIT, and also an astronautical engineering degree from the US Air Force Academy. I will now hand over to Larry, who will go through his presentation. What I would ask is if you have a question during the talk, put it in the chat. And if it's something that's really important for clarification, I'll let Larry know. We'll stop and we'll take the question. Otherwise, we'll take the questions at the end of the talk, and there will be some time for questions. Thank you very much. Over to you, Larry.
Well, great. Well, thank you, Evelyn. And again, thanks for all of you to attend. It's quite a distinguished group, and certainly always a challenge to talk to MIT grads. They're always full of questions and knowledge, but it's fun. And so looking forward to just sharing a little bit. Really, the talk is only going to be about my views on the role of space and how it has grown in the last 50 years, frankly, just based on my personal experience. But I think it cuts across a large swath of things that we are dealing with today. And it's just amazing in my mind to see how far we've come in really 50 years from a space capability, space enterprise perspective. So obviously in that amount of time, you can't touch on everything, but I'll start out with a little bit talking about the early days of PNT, position, navigation, and timing, talk a little bit about satellite command and control, early days and moving forward, talk a little bit about the intel community. One of my positions was I was the director of signals intelligence for the National Reconnaissance Office. So I pulled up some unclassified words from like 1970, but at least I can talk about it. And then touch a little bit on just NASA and space exploration in the various areas that we're currently working in that arena from NASA's and JPL's perspective. So that's kind of the outline of the talk. I'm going to try to share some slides here, and this should all work. So we'll give it a shot. If you'll bear with me for just a second. Okay. And let me know if you see those slides.
Not yet. Larry, give it a minute. It did come up quickly before. Noreen, jump in if you've got any advice.
Hold on a second. Let's see here.
It's coming up as just black, Larry. I don't know if you want to try and stop sharing and share again. No, now we can see it. It's come up. Maybe it was just slow.
Okay, so you can see it now?
Yes. We can see the presentation now. It's just not yet full screen.
Yeah, I hit slideshow and it doesn't seem to want to do anything. So you never know what's going to go on with Zoom or whatever we're on here. But Yeah, I tried turning off slideshow. Let me just stop sharing, and because it's a little bit easier. I'm going to stop sharing and try to do it again, and otherwise we'll just run with this if it works. So I
That's fine.
assume I've stopped sharing, and so let's go back. Let's share
The only difference
content.
now is we're recording, but who knows? Maybe that makes a difference with Zoom.
Yeah, you never know.
Okay, that came up more quickly this time.
Okay, and now I need to get the slides up. See the
Yeah, that's good.
slides?
Yeah,
Are they in screen slideshow mode or just?
they're not. They're not full screen. I did see there was a comment in the chat. Someone was saying you need to click the triangular from beginning play button.
Got it. There we go. How's that?
Perfect. Thank you.
Okay. Yeah. Sorry. I did know that and I just forgot. Okay. So again, I've kind of given you the outline and we'll just jump right in. I thought the first slide, appropriate for MIT people, a lot of text and a lot of engineering and science jargon. But really what I'm highlighting here is this was my first introduction.
Sorry, just to interrupt you. I think, can other people see there's a video picture in the middle of the slide, or is that just me? I think the Zoom camera might be covering the slide partly, or is that just on my side?
I'm seeing you covering part of the slide.
Yeah, I don't want to see myself. I'd much rather see Larry's slide.
You can
I don't know if
maybe,
you can move the little Zoom box out of the way. Is that possible?
I think it's people who are talking show up. So maybe mute yourself.
Okay.
I mean, I can turn my camera off if that helps anything. I don't know. Let's see.
I think it's that little box that's coming. Can you just minimize that box? You see how I'm in the lower corner? If you just click minimize the screen, I think that will get rid of it.
I don't know. I mean, you appear on my screen, but oh, hold on. Let me just try that. Let's see here. Okay, let's try that. Go
Perfect.
back.
That looks promising. Oh, I'm back again.
Yeah, whenever I go to the slides, you pop back up apparently. And whenever I click on to minimize it, are you seeing the slides when I'm in this mode?
No.
Okay. Because I have to go back. Now, are you seeing the slide with your picture on it?
Yes, that's what I'm seeing. All right. Well, maybe let's carry on and just move the screen out of the way. Yeah, there we go.
Yeah.
Perfect.
Okay, I slid you off to the side. Okay, interesting.
Excellent.
Okay, so anyway, going back to the early days of frankly navigating in space, this was the first project I worked on as a young officer in the Air Force. But essentially, we were trying to determine, how do we autonomously navigate the shuttle? Because GPS really didn't exist then. This was a paper that was written in 1977. I started working on this project in 1978, and we actually flew this experiment on the Force Shuttle mission STS-4 in 1981, 82 timeframe, as I recall. But essentially, we're saying, hey, how do we autonomously navigate in orbit? And the shuttle gave us a platform to do that. And so the concept was essentially a sextant. So we built, this was with Martin Marietta out in Denver, we built a autonomous set of 2 telescopes that on a gimbaled platform that could basically shoot the limb of the moon and a bright star, a known star. And by knowing the ephemeris of the moon and the location of the star and the time of the shot, then you start to get enough knowledge to put in your Kalman filter to autonomously determine your position. So that's what we were trying to do in 1978, 79, 80, 81 to improve our ability to navigate autonomously in space without relying on ground-based radars and optical systems. So we flew that on STS-4. I would say that partially successful. Back then, space hardware was not necessarily as robust as we had hoped, but we proved the concept, but we didn't necessarily prove it robustly nor to the accuracy we had hoped. But we learned a lot in terms of trying to do this autonomously in space. And of course, the next thing that came along was GPS. And I was fortunate enough to work on the early days of GPS. So on the left, you see a Block 1 GPS satellite, which was really the Block 1s were the spacecraft that were R&D. We were proving out the concept. We were proving that we could indeed get precise timing on board the spacecraft, significant enough to allow us to, put all that together from the signal coming down to the Earth and ultimately navigate on the Earth with a very, very, frankly, in the noise signal coming from the spacecraft at medium Earth orbit. So the intent was to build and launch 11 of those R&D satellites to give us enough of a constellation, which allowed us to, basically in certain locations on the Earth, we optimized it so you had at least 4 spacecraft in view and we could test the system on the Earth. Primarily did a lot of that at Yuma Proving Ground there in New Mexico or Arizona. And so that was the deal. And so I was a part of that team that completed and launched the last 3 R&D spacecraft, GPS 9, 10, and 11, and then was responsible for managing the program to develop the first operational spacecraft, GPS Block 2. So that's the capability or the spacecraft you see on the right. At the time, we awarded a contract for 28 GPS satellites because, again, we needed a constellation of 14, ideally, to give us the global coverage we were looking for. And at the time, that was the largest spacecraft contract in terms of by numbers that had ever been done. Rockwell and Seal Beach won that contract, and they were the folks that put the first Block 2 spacecraft together that gave us our initial capability. So again, if you know anything about GPS, you'll see the L-band antennas there in the center. You'll notice a big, see that red circular telescope looking thing. That's actually an optical sensor that the secondary part of our mission in GPS was to look for nuclear events. And so we had an optical sensor and a dosimeter on board that would look for nuclear events. So, very important for the nation, should there ever be one, to be able to track that very effectively. And interestingly, over time, we developed some new capability. We called it a W sensor, but it was essentially a sensor that could detect EMP. And with that EMP detection, we could actually locate nuclear burst pretty darn accurately, much more accurately than we could with the optical sensor. So just kind of an interesting adjunct to the GPS system, and there's still that capability on GPS today. So, but then, this was like, 1983, 84, 85, 86, that we still really didn't have an operational GPS platform, but obviously today, it's changed the world, and I think we all recognize that. We certainly recognize from the positional capabilities that we provide, but just as importantly from the timing capabilities that are provided by GPS that, frankly, systems all over the world rely on. And interestingly, we had in the US, we did a little exercise called the Day Without GPS, and just trying to kind of run through scenarios that says, okay, should GPS go away? What would be the impact across not just the military, but the commercial and civil community? And as you might imagine, it's pretty dramatic. So a very important system, really changed the world in terms of how we operate across a whole domain of things. And still, continues to be upgraded today. And I'm very fortunate to be able to, I sit on the United States Position, Navigation, and Timing Advisory Board. So this is the advisory board that advises basically the cabinet level secretaries in the US on the future of GPS, where do we head from here, and so on. So again, a great thing to be a part of in my past, frankly. A little bit about satellite command and control, at least from the Air Force perspective. This is a picture from really in the 90s or maybe late 80s, but we're, from a military perspective, we're starting to launch all these spacecraft. We've got a bunch of GPS satellites in orbit. We've got now missile warning satellites in orbit with Defense Support Program. We've got military communication satellites. So the Air Force said we really need to bring all of this command and control capability together. So they created a base to the east of Colorado Springs in Colorado, at the time called the Consolidated Space Operations Center, that resided at Falcon Air Force Station, ultimately becoming Schriever Air Force Base, named for General Bernie Schriever, who really, from a U.S. perspective at least, was the father of the modern ICBM capability that the U.S. developed in the late 50s and 60s. So that was really important from the U.S. military perspective, to bring all this C2 command and control capability together. And that allows you to kind of be efficient, be thoughtful about how you upgrade and share experiences and so on. And this is just, again, really from probably the 90s or 2000s. You can see that not the most modern displays or anything like that, but again, extremely important capability. And of course, we continue to upgrade and modernize and bring AI into that and reduce the workload on the operator and those kind of things. But again, just having that consolidated C2 capability for all the military assets was an important step in that. And, you know, another key capability is space domain awareness. Obviously, if you listen to Greg Novak here, Major General Greg Novak, who's the commander of Australia's Defense Space Command, he highlights space domain awareness as one of his key priorities. And this is just, frankly, a snapshot of some of the capability that's been available over the years. On the left, you see what we call a pave pause radar in the US, but it's a phased array radar that can track a multitude of spacecraft in orbit. In the center there, you see what we call the geode sites, but essentially it's optical sites that use optical to track spacecraft in orbit. And then basically the Space Telescope on the right, that's now here in Australia. That's an incredible and important component in the space domain awareness arena. You know, developed by MIT Lincoln Labs. I was actually pretty engaged in that before coming over here to Australia, but a very exquisite capability, and especially important for the Southern Hemisphere, and especially important for, frankly, its location in Australia and south of China. So really happy that that capability is now extant here in Australia. But again, it's a worldwide capability, and you know, everyone talks a lot about low Earth orbit and the number of spacecraft. I gave a talk yesterday, and they were talking about, is the Kessler effect started, which is, you know, theoretically this chain reaction of spacecraft running into each other, and you totally destroy LEO, etc. So understanding the LEO environment, understanding where all these spacecraft, both operational, dead, debris, etc., are, is absolutely essential as we move forward, especially as we develop, you know, commercial capabilities more and more in LEO. And so that kind of led on the left to the Joint Space Operations Center at Vandenberg Air Force Base. I was the colonel who stood that up back in 1998. And it's obviously grown by leaps and bounds since then. It's now a consolidated space operations center with multiple services, multiple nations. Australia has representatives there. They continue to grow in terms of their automated capability to manage this sphere of operations in space. And they do it very well. I put a very obligatory picture down there on the right with there's a competition that the military has on who are the best space operators across a multitude of capabilities. And these folks at the Space Operations Center won that award quite a few times. And you can see me there in my lovely uniform on the right. But yeah, just so important today, and will continue to be important. You know, in the presentation I gave yesterday, one of the questions was, you know, how are we going to manage these large mega constellations? How are we going to ensure that, you know, everyone can still operate freely, especially in low Earth orbit, as those constellations continue to grow, both commercial, civil, and military? And how do we deal with the debris? And those are all important questions that all the nations need to manage. In fact, you know, if you're familiar with the IAC, the International Astronautics Congress, big deal for the space community. They just completed the IAC in Milan a couple of weeks ago, but the next IAC is going to be here in Sydney. And one of the things that we're trying to develop is a what we call a zero debris agreement for the Indo-Pac countries to sign up to, that could be announced at the IAC next year. So, Europe has done a pretty good job of getting nations to sign up to say, look, as we develop new capability, we'll make sure that there is no debris from our spacecraft or from our rockets. We either put it in safe orbits when it's done, or we re-enter it. And we're trying to do the same thing here to get Indo-Pac nations to kind of agree to the same thing. So definitely an ongoing area of operations and importance for all spacefaring nations. So that's a little bit about space domain awareness. I said I would touch briefly on the intel side of things. Just for your awareness or knowledge, you may know this, but in terms of space capabilities for intelligence purposes, those are generally managed in the US by the National Reconnaissance Office. So they develop imagery spacecraft, they develop communications for those systems, and they develop signals intelligence spacecraft. And that's the role I played. I was the director of signals intelligence there, with my primary customer being the National Security Agency, NSA. And this is just an unclassified thing that's been declassified, which is really the first US signals intelligence spacecraft that we developed, frankly, to look at the Russian order of battle from an electronic perspective. You can see some of the words there, but if you recall, back in the 60s, we were flying U-2s over Russia, and Francis Gary Powers got shot down, and the US pushed pretty darn hard to say we must get capability in orbit to do that. And I thought it was interesting, that second paragraph, and this is all out of an unclassified report that's been released, but Sputnik 1 was launched, but the US was already pretty far along in terms of building reconnaissance satellites, recognizing the capability they would provide to provide for the national defense. So even though people talk about Sputnik being a surprise, and certainly in some ways it was, the US is already pretty far down the road in terms of the ability to put things like the Poppy spacecraft up into orbit. So again, I can't go into a lot of detail on anything else, but just recognize that a lot of technology development has happened in the last 40 to 50 years, and these are incredibly capable spacecraft. So I'll leave it at that. But it's a big component of the US, if you will, infrastructure in terms of the civil side of space, which is NASA, the military side of space, which is now the Space Force, but the intelligence side of space, which is the National Reconnaissance Office. So it's kind of a three-legged stool from a government perspective in the US. So we'll move on to exploration, if you will, kind of the NASA mission. I like these slides. You'll see one for planetary, you'll see one for earth science, you'll see one for astrophysics. And I recognize you can't necessarily read all of those, and it's not my intent, but just to highlight the wonderful abilities and numbers of spacecraft that are out there doing planetary exploration. And these are not all necessarily U.S. spacecraft. I mean, Bepi Colombo is ESA, Envision is ESA. So we tried to capture, who's out there looking at the moon or the planets and doing science. So I'm just going to highlight a few of these. And of course, I would be remiss if I didn't talk about our operations on Mars, which has been a key focus for NASA for 40 or 50 years. I still get updates from JPL on what the Perseverance rover is doing. So this is a picture from about 3 days ago, where we are transiting the rover up to the top of the kind of the crater rim that we landed in to take samples and ultimately bring them back to Earth. But you can kind of see the back end of the rover there as the camera looked back to look at the tracks going through the valley there and heading up the crater rim. The veins you see are just cooling veins for the RTG that powers the rover, so the radioisotopic thermonuclear generator, which is plutonium. So incredible work on Mars. JPL's been at Mars with orbiters or landers or rovers for about 45 years. So it's been a continuous presence either around or on Mars. And up until the Chinese landed on Mars a couple years ago successfully, JPL was the only organization on the planet that had actually landed successfully and operated on Mars. So they were pretty proud of that fact. But continuing to do amazing science. really, as I said, Perseverance primary mission is to collect samples to bring them back to Earth eventually with the Mars sample return mission, which frankly has had some budget issues and is kind of in a period of rethinking. But Perseverance continues to collect samples. I think they've got about 10 tubes still open for them to collect. And essentially, it's a science team that's constantly looking at the environment and the geology in the area they're in and determining, is this an area we want to dive deeper into? And ultimately, is an area, do we want to take samples? And so they're constantly doing that evaluation. And then they then instruct what we call the rover drivers to, okay, we need to go over to this particular rock. Please build a command set to do that. The rover will execute that, and then we'll operate there in that environment to bring the robotic arm down close and do some scoring of the rock and determine, do we want to sample or not, and do a core sample. So ongoing mission every day, extremely busy, and reasonably high pressure to do all this on another world. So that's just a little snippet. I can talk all day about other missions, Psyche, Europa Clipper, whatever, but we can get to that in Q&A if you want. I want certainly to allow time for that. So this is astrophysics. Obviously, one of the hot topics these days is exoplanets. If you're familiar with the Kepler mission that JPL built several years ago, allowing us really, for the most part, for the first time, although I will say, you can use star wobble and various other things to determine there's exoplanets there, but in terms of the ability to really find a lot of exoplanets, Kepler was an incredibly important mission and has identified thousands now of exoplanets and quite a few within that Goldilocks Earth zone, if you will, around other stars. So this is going to be a whole big focus for the astrophysics community going forward, ultimately to image Earth-size exoplanets. And of course, when you image them, you can get the light, which you then can break down in this, spectroscopy, using spectroscopy to look at the light components and ultimately determine, do I have lines of nitrogen? Do I have lines of oxygen? And that can give a lot of insight into, could there be life processes happening on another Earth-sized planet? So that's kind of the big goal in the future. The next big telescope for NASA, you're probably all familiar with James Webb, doing an incredible job. Doing some exoplanet work as well. This is the Nancy Roman telescope. Its primary mission is to really look for dark matter using galactic lensing to understand the variations that could be caused by dark matter using the galactic lensing. But its secondary mission is to, again, try to image exoplanets that are probably Uranus, Saturn, Jupiter size, not necessarily down to Earth size, but the key component for that is a coronagraph. So a coronagraph is just a device that masks the light coming in from the star into the telescope and blocks that starlight in such an effective way that you can actually see the reflected light from the planets orbiting that star. And this is the coronagraph that JPL built. Extremely complex device, so many light paths. It's just an amazing thing. But ultimately getting down to like 10 to the 16th or 10 to the minus 16th or 17th, basically blockage of the starlight so that you can see that faint light from the planets. And that's been built, it's been tested, it's been delivered to Goddard Space Flight Center in Maryland, who they're putting a telescope together, and the telescope should launch here in the next year or two. So exciting mission for the dark matter people, but also an exciting mission for the exoplanet people. So just a little snippet of what's going on in the astrophysics world. And then, of course, Earth. When people talk about NASA or think about NASA, if you're not really familiar with NASA, a lot of times you will, they'll think, okay, Mars, rovers, helicopters on Mars, outer planets, telescopes. But the reality is Mars, or NASA and JPL do an incredible amount of work for Earth science. In fact, I was just communicating with the lead Earth scientist back at JPL yesterday, and I asked him, well, in terms of understanding our climate and understanding what's going on, what is the percentage of data that we get from space that allows us to do that? versus other sources, whether in situ sensors and just local sensors and those kind of things. And he essentially said, well, if you just look at the quantity of data, not necessarily what it's used for and so on, or its importance, but he said probably the quantity of data, it's probably 99% of the data that we get to assess our climate and environment comes from space. Now, again, there's in situ sensors that are important that, even though they're 1%, they're extremely important, et cetera. But if you just look at the quantity, because we're bringing down so much data, whether it's radar, hyperspectral, whatever, just an incredible quantity of data. So if you look at just the quantity, it's probably 99%. So I thought that's an interesting little factoid in terms of what space does to help us understand our changing environment on the Earth. So I'm just going to highlight a couple of missions that I think are very important. And this is the NISAR spacecraft. That's the NASA ISRO, Indian Space Research Organization, synthetic aperture radar. So it's a joint project with India. The first time that NASA has done that, first time JPL has done that. And it really is a 50-50 partnership. You see the payload there on the right without the big radar reflector antenna that goes on top of it. But here's the payload getting ready to go into the thermal back chamber in India. And so, again, they built half of the radar. They built the L-band. We built the S-band. We integrated the payload at JPL. We then shipped it to India, where they built the satellite bus, which you can see on the bottom there of the payload, that square object. And they integrated and tested it and got it ready for integrated tests. And we're on track to launch that early next year. So again, extremely important for Earth science because of that L-band, S-band SAR. You can look at biomass changes. You can look at shoreline changes. You can look at ice mass changes. So you really start to get this changing map and the dynamics of, frankly, the Earth's surface using that combined L-band, S-band. So Earth scientists are very excited about that. And as I said, should be launched early next year. Another, what I consider to be a very important mission is understanding the water cycle for the Earth. This is an artist's depiction of the SWOT spacecraft, surface, water, and ocean topography. So this is a new technology built at JPL where we're using basically 2 radar beams and radar interferometry to measure ocean height, which we've frankly done for years with microwave radar. But the problem with microwave is it does not reflect off of fresh water. It needs the saline content in the ocean to reflect. So we've been able to measure ocean height and ocean height changes for decades using microwave radar from space. But with the radar interferometry capability, I can now get reflections from freshwater bodies. So this is the first time that we have been able to now globally map freshwater bodies and build that capacity and build that understanding. So now we're flying globally over, I think, the globe every 13 or 14 days, as I recall. And you can see reservoirs, you can see lakes, you can see rivers, you can get some sense of the river current, and you look at the height and what's going on. And so the scientists are very excited from a water dynamics, water ecosystem perspective, because now they're going to be able to build this global database, which allows us to understand the dynamics of freshwater, just as we've understood the dynamics of the ocean and saltwater for decades. So that was launched in, I believe, 2020, as I recall, maybe a little later, but operating very well. And I will say, just like we had the partnership with India for NISAR, this is a very important partnership with CNES, the French Space Agency. So JPL provided the radar and, figuring out how to align those 2 beams to microns across that big beam there you see. And then the satellite bus was provided by the French Space Agency. So extremely important partnership, extremely important capability for the world to understand the water cycle. And this is kind of one of my favorite Earth science spacecraft. It's called GRACE. Essentially, it's a gravity change measuring satellite. And when the engineers and scientists came up with how to do this, it still boggles my mind in terms of the technology and the thinking that went into this. But you say, well, how do I measure changes in gravity from space? And essentially what these two satellites do is they fly in formation a couple hundred kilometers apart. And you can kind of see the little beams between the two spacecraft, but using microwave and laser beams, they measure the exact distance between those two spacecraft, generally down to nanometers. So you are having this extremely precise measurement of the distance between the two spacecraft. And so what happens is, as the lead spacecraft flies over the Earth, it flies over changing mass profiles. So if the lead spacecraft is flying over the Alps, there's a huge amount of mass there that actually pulls the spacecraft forward faster, and it creates a separation distance between the trailing spacecraft. And so as the trailing spacecraft comes over the Alps or Mount Everest or whatever, it catches up because now that mass is pulling on the trailing spacecraft. So as these spacecraft are flying over the Earth, they're constantly changing the distance between them, but it's based on the mass beneath the spacecraft that is essentially accelerating the spacecraft. And so over time, you build this global map of mass locations, if you will. And then over time, as you fly over that same spot, if you sped up less and the distance changed less, then there is less mass there. So a great example I like to use is the Central Valley of California, which is really one of the key agricultural producing areas in the United States. It frankly relies on an underground aquifer to provide water for all the crops. And using these two spacecraft, we've been able to measure that underground aquifer change very accurately by the change in mass. So as they, especially in drought years in California over the last decade, and as agriculture has expanded, they've continued to draw down the water in that underwater aquifer. And really the only way you can understand and see that is with these spacecraft, because it's very difficult to drill down thousands of meters and try to do it all over the aquifer and figure out what's going on. But this can tell you that, hey, 20 years ago or 15 years ago, this amount of mass was there, but now there's less mass there as I fly over it. So it's a very powerful tool. I mean, you can look at all kinds of different changes from a mass perspective that, ice sheet changes over Greenland and the poles, et cetera. So just an amazing earth science capability. Again, a partnership, this time with the German Space Agency, DLR. So I think that also gives you a sense of just the international partnership capability that's very important in any space endeavor these days, in my opinion. And then I'm going to finish with this because it's kind of finishing on a high note for Australia, but this is a lot of things that are going on in Australia. And that's really one of the reasons that I elected to kind of move here and live here was it's a burgeoning space community. It's an exciting space community, a lot of things going on from a startup perspective. Frankly, a lot of challenges too with government funding and really what is the strategy of Australia here, and can we build that ecosystem that we should have as a sovereign nation. But on the left, I highlight the Kenyani spacecraft or Kenyani spacecraft that was funded by South Australia, built by SmartSat as the program manager and Innovar as the payload provider, but just launched a couple months ago, a month and a half ago. So really a capability now that's coming to fruition in Australia. It has a hyperspectral sensor on it. It has a tactical comm experiment on it. So things that can provide value for Australia in the form of a CubeSat. On the right is Waratah Seed, which is Sydney Uni's spacecraft, which launched about the same, I think it was on the same mission, the transporter mission for Falcon. Again, showing that indigenous capability here in Australia to build missions and capacity. Lower left is Space Machines Company there in Sydney. Again, kind of a startup organization, a couple of MIT grads actually that are putting it together and launched their first, frankly, small sat, medium-sized sat capability that Australia has ever built. They launched it last year out of Vandenberg, and they're on the path to build much more. And so I think that's historic in terms of Australia's capability to do that. And then the launch sites that are all being developed around Australia. I believe a lot of people think this is going to be a key focus of endeavor for Australia with launch and return. In fact, I was meeting with a startup company a couple of days ago Forgot their name, Bardon or something like that, but essentially they're a pharmaceutical company in space. So they are developing pharmaceuticals in space that you can only develop in 0G for targeted medicines. And they're going to re-enter those pharmaceuticals here in Australia and bring them back to Earth, and then look at building capacity and deploying those into the healthcare industry. So a lot going on in Australia, exciting time to be here. I think there's still challenges in terms of the strategy for Australia and what is Australia really going to do in this domain from a governmental perspective. And I think, funding is still challenging with VCs and those sorts of things, but I think it's an exciting time to be here. And so I think that's my last slide, except for that one. And that's just highlighting, if you've watched the news and you're a space geek, you saw that we launched the Europa Clipper mission about 10 days ago out of Cape Canaveral on a Falcon Heavy to explore that moon of Jupiter called Europa, which is, we believe, a water moon with 2 to 3 times the amount of water beneath its icy surface that the entire Earth has. So pretty incredible. And going back to like the beginnings of my career, 50 years ago, we thought probably the Earth is the only planet in the solar system with water. And now we find water and ice all over the place. So dramatically changed our perceptions of possibilities of life and how the solar system was formed and those sorts of things. So exciting times. So I will stop sharing. I think I can do that. And then Evelyn, if there's questions, we can jump to those.
Absolutely. And Larry, feel free to turn your camera back on. Thank you for bearing with us with the technical challenges. I see that there's one question in the chat. If anybody else has a question, please raise your hand. You do that with the reactions button on the bottom if you're not used to Zoom. I don't use Zoom too much personally for my work, so I have to always find things. Otherwise, feel free to put a question in the chat. The first question we have, Larry, I don't know if you can see the chat now. Dan had a question about the intelligence satellite and if those were solar panels on the outside.
Yes, those were, just the way they built it back then is just small solar panels that powered the spacecraft. That's absolutely right. Yeah. And I see, how does Grace isolate gravitational effects from non-gravitational forces? Yeah, I mean, that's exactly the right question. And I will tell you that there's extremely accurate sensors on board. There's extremely accurate GPS sensor, receivers on board. And so, the engineers and scientists have absolutely accounted for that. They look at the atmospheric models. All that goes into their algorithms to take those things out of the equation, if you will. And what we have left in terms of the separation change is absolutely due to gravity. But the Grace mission has been we're in the second iteration of the spacecraft, so they've been flying for a couple decades, and we continue to improve them and move to better measurement capabilities. But the engineers and scientists understand pretty well how to take out those components with the very accurate sensors and the GPS capability they have on board. So but it's absolutely the right question.
Great. Feel free to raise your hand if you've got a question. I've got one for you, Larry. Something that's always been a challenge, and it was really interesting to see you mention that new satellite that has the capability to look at fresh water. But most of our planet is covered with water, and it is still to this day really difficult to get good, accurate maps of the seafloor because of the problem of seeing through the water. Do you have any thoughts on that?
Well, I mean, to be honest, that's not a problem that can be solved from space, in my opinion.
We've got to do it here on Earth.
Yeah, it has to be. I often hear the comment that we know far more about Mars and its surface than we know about our ocean here on Earth. And I think that's a true statement because nobody's really set out to map the undersurface of the ocean, right? And because it's hard. I mean, you just can't put a sensor that looks through all the water and give you a large swath of map. So, that's not something we can do from space. That has to be in situ. It's probably pretty expensive if you want to map large swaths of the ocean floor, and you would have to have a reason to do that. I mean, you probably know better than I. I'm sure there's general maps, right? We know where the trenches are and all those things. And
yeah, and there are efforts trying to look at that, but it is interesting. And I was just thinking about it. I mean, if you think it's expensive here on Earth, but if you're going to these moons that have water and things. I mean, do you need to build submarines ultimately to really do the exploration? It's an interesting question to think about, and certainly
And people are. I mean, we talked about Europa. I mean, the first Europa Clipper is basically it orbits Jupiter and it flies by Europa because you can't orbit Europa because the radiation environment is just too intense. You can't stay there. But we fly by it multiple times. But the next phase would be a lander to go down and just examine the ice directly and scoop some ice up and see what you find. And after that is going beneath the ice. And people have been looking at, thermal powered, heaters to go down. I mean, it's possibly a kilometer or several kilometers thick. So how do you even get through the ice to get to the water? Or how can you find crevasses to go down? And so that's the next 2 generations of thinking in terms of what do we want to do. But yeah, ultimately you got to get to the water.
Yeah, interesting.
Okay.
I see Sam has a hand up. Sam, why don't you ask your question, then we can go back to the chat.
Yeah, hey, this was fantastic to hear about your history and your experiences. I would love to hear your reflections on something that I'm curious about. Do you think that there is a watershed moment in the future for when the development of positioning, navigation, and timing systems for cislunar space will begin to be of interest, not just to like governments, but potentially even like private industry? Because that's something that crosses my mind a lot as something that might not even happen in my professional career, but that I'd love to see start to tip in that direction. So whatever reflections you have on the development of PNT for cislunar space, I'd love to hear.
Oh yeah, I mean that's actually a very relevant topic today. I mean, NASA wants to go back to the moon with astronauts, soon. They ultimately want to basically stay there, just like you look at the Antarctic McMurdo Station, those kind of things. So, that's the intent. And absolutely, I mean, I think Lockheed has already spun out a company to do comm and positioning over the lunar landscape. Yeah, so they already recognize that is going to be a need. We think we can provide a service that will make money for us. And it won't ultimately just be for NASA, in my opinion. It will be for commercial entities and others who are going there for whatever reason. Or science or whatever. So yeah, I mean, the whole comm and nav thing in cislunar is absolutely already happening in terms of designs and people thinking about it and looking at how they create capability with small satellites and so on. So yeah, that's absolutely, in fact, here in Australia, interestingly enough, under, again, part of my job is working at the SmartSat Cooperative Research Centre, but funded by SmartSat was developing a low power waveform that you can use for communication as well as location. And NASA has actually taken that and put it in as a requirement in their Artemis requirements to say, use this waveform. It's low power. We can kind of do RFID on assets moving around the moon. We can figure out where they are, et cetera. So yeah, that's definitely a burgeoning area that will continue to grow and will happen, in my opinion.
That's great. Yeah, just always wanting to understand like how competitive and how much it's heating up, and just exciting to hear. Thank you.
Yeah, I mean, NASA will be the first customer. I think it's an open question of when there will be kind of other entities there needing it. But given the cost of launch going down and Starship, easy to get places, I think people will go out there and do things commercially. So
thank you.
Yeah.
Great question, Sam. Thanks. We'll go back to the chat, Larry. This one, I don't know if there's a security issue with this potential one, but we have a question. If a major war breaks out, should we expect to use civilian GPS right away? Now for this one, I'm very glad that I'm a geologist and I did all my training having to map without GPS because I might still be able to navigate. But it's true in our modern world. It's it's quite a challenge, isn't it?
Yeah, I mean, certainly jamming GPS signals. I deployed for Iraqi freedom, and the Iraqis were jamming GPS signals in that environment. If you look at the war in Ukraine, there's GPS jamming going on there. So jamming GPS is not super hard. As I mentioned, the signal is down in the noise. So you don't need a big, powerful transmitter to jam it. But certainly, I think the ability to navigate will be attacked. Will it affect all the civilian world? It's difficult just because right now I lose track. Probably at least have 30 GPS satellites in orbit, and they're in MEO. They're in medium Earth orbit, so they're not low Earth, so they're not all that easy to get to. I think there will be some desire, probably with just more local jamming, to take out GPS, just because it's pretty difficult to take out the entire constellation. So if there is a conflict in the South China Sea, if you're operating in that area, my guess is you're going to lose GPS. But if you're in the U.S., my guess is you'll be fine, because it's just hard to attack, a full constellation of 30 spacecraft in MEO, my opinion.
That's a great question. It reminds me, recently my son is 7, and I was explaining to him that there was a time before GPS, and he didn't quite understand. And so he said, well, how did you get anywhere? I said, well, we had maps. And he's like, maps, like paper maps. And I said, yes. And his only reference, he said to me next, he says, Mom, you mean like a pirate? And I said, yes, exactly, like a pirate. So I thought that was a good explanation, because for him, he had no other concept other than his storybook of how anybody would navigate without their smartphone.
Well, and people also say, well, I don't need satellites to navigate. I've got this thing, They think it's all inside the phone, right? No, that's just the receiver. But yeah, it's that, the general public thinks, well, my phone does everything for me. What's a satellite got to do with it?
Great. Okay, well, let's continue with the questions that we have in the chat. So the next one was a question about Boeing's future as a space service provider.
Interestingly, I had this question yesterday. Must be a topic on a lot of people's minds. But my answer then was, and they were kind of contrasting to SpaceX and what's going on with, SpaceX is launching Dragon capsules, Boeing can't get their capsule built, et cetera. I do believe that, this is just my opinion, right? I don't have any great insights into Boeing. I mean, I've worked with Boeing and those kind of things, but Boeing is a huge company. Over time, large companies tend to accrete process and structure and regulation, versus like a SpaceX, which, is pretty agile and vertically integrated and can respond quickly to changes and failures in market. And I think Boeing they've lost their ability to be agile. They have just complex structures that are trying to do all this across many, many teams, et cetera, whether on the space side or the air side. They've got multiple supply chains they have to deal with, which adds complexity. So I think it's just a combination of those things. I think Boeing can right the ship. They're smart people, they're good people, but I think they probably have some tough decisions to make to sort out how do we get better at this in this changing space environment, especially with lots of new entrants, lots of people that are lean, lots of people that are vertically integrated, and they're just moving fast, and Boeing has to figure out how to do that and do it successfully.
Great. We've got a couple questions from Roger. The first one, I don't know if you can read it as well, Larry. I'll do my best. He says, for the mission that includes Starlight to look at reflected spectra from a star's planets, how is this done to further take into account that the light from the star and its planets will be subjected to gravitational lensing and diffraction effects from a meteorite, dust clouds, etc.?
I think those things. And again, I'm not a chronograph designer, but I'll speak to as much as I know. But for me, the bottom line would be, all you're trying to get is the light into the telescope. And there may be smarter people on this call that can answer better than I can. The gravitational lensing, we're not really worried about the location of the planet when we're doing this, but scientists know how to take that into account. But it's more about just getting the actual light into the telescope. Because once you get the light, whether it's the starlight or if you block the starlight and it's from the planet, then you can do the spectroscopy. So that's the important thing. And then, and the diffraction effects, well, again, you take that into account when you're capturing the light with the telescope. You want a big telescope so you can capture as much light as you can. You focus it on the focal plane array and you do your thing. So those are things that all kind of just come out of the fact that you're just capturing the light. So that would be kind of my answer there. But if there's smarter astrophysicists on board, they can easily answer that too.
Raise your hand if you're an astrophysicist and you want to explain it to us. But that was a pretty good answer, Larry.
Yeah.
Roger had a second question. He said, When do you think we will see a US launch vehicle launch from Australia?
Well, again, your crystal ball is probably as good as mine. I read, reports just like you probably do of, Elon talking maybe about bringing Starship over here and so on. I think there is a fair amount of energy from the U.S. perspective, both governmental and commercially, and perhaps civilly, NASA, to say, hey, Australia's building infrastructure. There's capacity there. Let's look at that. And I think Elon is certainly serious about it. And again, once we're successful in showing, successful launches out of Australia, then I think the U.S. market will be looking at, it has to make sense from an ROI perspective, because you got to pay to ship the rocket across the Pacific or whatever and all those things. But, Elon started launching out of Kwajalein, right? So, he was willing to do that when he was first building the Falcon rocket. So I think it will happen. I think maybe the first person to do it would be SpaceX, just because when Elon's interested in something, he figures out a way to make it happen. So.
Great. Next question we have is, can GRACE data assist in studying tectonic activities and earthquakes? I might be able to help with that one, Larry.
Yeah, well, I'll make a general comment. From a tectonic and earthquake thing, it would really be if mass has shifted significantly enough to basically impact the spacecraft that it's flying over. So I'm not sure that's doable, but certainly Evelyn, take the ball from here.
Well, certainly having better gravity data over the Earth will help us understand what structures are located beneath the Earth, what types of rocks, what things are likely to happen. So in terms of actually physically watching an earthquake happen or tectonic activity happen, there's probably better instruments. But in terms of understanding the structure of our planet and better predicting where you might have activities, the data must be very useful.
Yeah.
Great. Then we've got 2 more questions, and then we'll probably wrap up because we are close to the hour. So the next question is from Toby. What types of applications for scanning, measuring, mapping technologies do you wish to see or foresee in the future?
Yeah, a pretty broad question. If you think about especially Earth science, let's start there, measuring the Earth. There's a host of things we want to continue to measure and measure better. We measure carbon dioxide from space. We measure, when you do hyperspectral, you're getting these hyperspectral cubes that look at a lot of different things. One of the missions we have on the space station is looking at minerals with hyperspectral capability. So, I think the fundamental frequencies that you're looking at are not going to change. It's IR, it's HSI, it's optical, primarily as you think about these things. It's just getting higher fidelity capability, higher swath capability, whether it's radar or in the other frequencies, and continuing to improve on that. And then I think it's about the downstream application and capability to ingest all of that data and make meaning out of it in some kind of rational way without destroying the computer infrastructure. I talked about NISAR. That's going to create 78 terabytes of data per day, like the radar system. So, just dealing with that quantity of data, either managing it on board, applying some ML and AI there, or getting it downlinked to the Earth, large quantities, those are the things that I think will also challenge us as well. And so that's, but I think it's just going to be more and more improvement in capability. It's going to be in the various frequencies we're already operating in, or radar as well. It's going to be miniaturization of a lot of those instruments, which has happened over the last 30 years anyway, but you're going to see more and more. So I put more and more capacity on small spacecraft. I have more and more fleets of spacecraft doing these measurements, so I have better understanding and more real-time data. All those things I think are going to be some of the key things for the future.
Great. Then the last question that we have in the chat is from David, and he asks, is there any work on satellite resource management's i.e. beam hopping happening in Australia, or is that work mostly done in the US and Europe?
Satellite resource management in terms, I'm trying to read exactly in terms of comms and so on. I'm not quite sure, but I don't know if I'm going to give a good answer here. I don't know, David, do you want to just
Do you want
expand
to
on that so
clarify
I
your question,
understand?
David? Are you still with us on the call?
Yeah, I'm just basically asking for my wife. She does optimization operations research work, applying mathematical techniques like integer programming to different problems, and she's very interested in satellite resource management. But it seems that most of the work is happening in Europe, Luxembourg, and maybe US Lincoln Lab. I'm not sure if that work is just done there and then sold to Australia, or is there any work that you know of that's happening in Australia?
Yeah, if you're talking, broadly about, okay, how do I manage and make efficient the satellite resources I have? How do I inculcate AI or ML on board and do things?
Yeah.
In that realm, yes, there is work going on in Australia from just a resource management perspective, making my spacecraft more capable on orbit versus having to manage things on the ground. I'll put my SmartSat hat on, but we've stood up an autonomy AI lab that's really indeed focused on that. You can do hardware in the loop and those kind of things and start to build out capability to say, let's be more efficient in managing this particular spacecraft or managing a constellation of spacecraft. I've seen some work going on with laser comm and how do we utilize that to flow data across and those sorts of things. So I would say, yes, there's absolutely things happening in Australia from that particular context.
Great.
Thank you.
Larry, if I may, I've got one last question from me. I was wondering if you have any comments or thoughts on the space tourism that has started happening in recent years, where these really wealthy people are becoming astronauts. To me, I find it challenging, compared to when I was a child, or my father talks fondly about when he was a child, and you sort of look up at space, being this place. I kind of think of it like Antarctica, you're going there. Obviously there's military applications, but it's mostly governments and space exploration. And now to have this commercialization and this tourism, to me, feels very strange and very different. Do you have any thoughts or reflections on that?
Yeah, this was another question that kind of came up yesterday in the talk I gave. But, I think NASA's vision, and I think the realities are going to be that you're going to slowly see a commercialization of low Earth orbit. I talked about pharmaceuticals, so there has to be a business return, right? But number one, cost of launch. It's dramatically reduced over the last decade, 2 decades. SpaceX has driven a lot of that, but you're going to see more and more of that. And that's always been the barrier, right? If I can get to space pretty cheaply, there's a lot of things I'd like to do in space in terms of manufacturing, pharmaceuticals, other things, research, that opens it up to much a broader swath of society and business. And frankly, along with that, once you get the cost to launch lower, then more and more people are going to want to go do it. People that, they're enamored with space, right? It's cool. It's Star Wars. It's whatever it is. So I think it's good. I think, the commercialization of low Earth orbit is going to happen. It probably won't happen as fast as some people would like. But, science and technology, in my opinion, continue to drive down the cost to get there and the cost to operate there. And eventually, your child or grandchild can probably buy a ticket for $10,000 and go up to a space station and stay there for a week for vacation. That's my guess.
That's cool. Maybe I'll be old enough to see that, or young enough to still see that happen. That's great. Although then we got to really worry about our carbon footprints of not just taking a jet across the ocean, but actually launching up into space. We need to figure that out as well.
And there's work going on with hybrid rockets, which are less of a carbon footprint, and there's things things happening in that arena too. Yeah.
That's exciting. Well, thank you, Larry, so much for your time, and thank you everyone for joining the call. Really appreciate it. For those of you who are here in Australia, we're going to have our next virtual coffee next month. I'll set out the invitation today, so keep an eye out for that. And then our talks will resume again in January. So we will see you all hopefully at our next virtual talk. This has also been recorded and it will be posted probably within the next 2 weeks up on the MIT YouTube page. So keep an eye out for that. And if you know anyone who wanted to see it, do feel free to share the link with them. Thanks very much, everyone.
Thanks everyone for your attention. Thanks.